All right, so let's see. So this we will try to motivate ourselves to understand how to numerically solve. I mean, how to numerically solve system of nonlinear equations. And there are two approaches as usual. If it is if it is more than three-dimensional problem involving three variables, of course you can't solve graphically. That's the limitation of graphical method. X, Y, Z, 3D space only you can visualize. If it so that's the limitation of graphical method. So one method where you plot two functions or three functions and see where they are intersecting. If it is a two variable, it will be a curve on the plane xy plane, and where the curve intersects, you can find the solution. If it is more than two variables, that is three variables, and we will see where the two surface intersect. Okay, that will be our Python uh, stuff we will do today. After we learn this analytically by hand, then we will move to Python and show that a complicated problem and how to solve using Python. Okay, I'm coming. Yeah. Anyway, the second one is the Newton Raphson method. Okay. What is that something more? What is the something more? Also known as multidimensional. Multidimensional Newton Raphson method. Because if you have just one method, right? And if you have just one equation, there is no meaning of computing nonlinear equations. If you have just one. If you are saying system involved to find the common root. Okay. Anyway, so suppose, let us build up the problem here. Suppose we have a system of nonlinear equations. F1, suppose it is of n variables, it has n variables. Okay, and n variables. So how many equations should I write? If there are n variables and you want to compute those n variables, how many equations should you have? An equation at most. You have f2 of x1, x2, xn, so on till fn of x1, x2, xn. System of nonlinear equations where fi's are nonlinear. Nonlinear. One good thing is the number of unknowns number of equations. Writing this whole stuff like a system of equation which takes up a lot of space, you can actually use something like a function. You can just write this in one line. Notation form, then I would say x is a vector, 0 is also a vector. Can you understand this thing? Then F, stylish looking F, this will be like a vector of F1, F2, so on, up to Fn. It's just a collection, X1, X2, Xn. And of course, this 0 is a 0 vector, 0, 0, up to so on till 0. Okay. So this is just by vector notation. You can just write in one line. Our aim is to solve this equation. So now can you get an understanding why everyone was chanting Newton Raphson? Because it is just solving a, isn't it? And you did in the second class, f of x equal to 0, isn't it? This is just that this is the vectorized form. Now, can you tell me what was Newton Raphson method? We start with an initial guess, then we apply Newton Raphson method to generate x1. Again, apply Newton Raphson method, we have x2, so on. And we generate a sequence of roots. It's a hope that x1 is converging to the. So, can you tell me what was the iterative scheme of Newton Raphson method? Xk plus 1 is equal to xk minus f of xk of f at sk. Okay. Now, this is for solving just a scalar equation f of x equals to 0. This is the normal Newton Raphson method. How to solve a multidimensional Newton Raphson method? Forward actually. It's pretty straightforward. How? So just follow my lead. I will write here. Here, instead of just a variable x, your x will be a vector because following this notation. So this is x, okay? And you have as usual, but instead of here as a scalar, vector, xk plus 1 vector, okay? That means the k plus 1th approximation of your roots. And this is equals to the vector xk as usual, but it's a vector. Fine. Minus any ideas. Of course, there will be the stylish looking f, which we have drawn here. Okay. And then you have just the evaluation xk as usual here, according to this. So I want you to make a correspondence between this formula and the new formula. It is quite similar, but just the case that you have now more dimension to it. You are storing everything in a vector. Okay, that's the idea. Now I ask you, what should be? Now I ask you, what should be? Another guy over here to be written down. It's the derivative, right? The derivative is missing. I did not write it yet. But do you think, can we use the normal derivative? No. Yeah. So, since it is just, previously it was just, therefore derivative worked. But since you have multiple, go to Jacobian matrix. What is Jacobian matrix? It's a collection of partial derivatives. Matrix made up of collection of partial derivatives. Later you will see it's usually denoted by J. But yes, I will, since you are starting it, I will start with a very nice notation known as df. Okay. What is df over here? Is that all? This is the stylish looking f and evaluated at the vector xk. And the stylish looking f, this is multiplied xk. Do you think it's correct? Is it correct? I just ask you to make an analogy between this and this. See, everything is vector. Otherwise, everything is similar. The derivative, we are just replacing it by Jacobian matrix. I will let you know what is the df soon. But tell me, just by carefully comparing each of this equation, are this okay? Is it okay? Okay. So, any ideas? Any ideas? Is it correct? I'm asking. I'm not asking anything new. Is it correct? No. Why? Something is there. Something is not falling on the right place. Of course. What is that? Of course. Of course is you have the derivative on the denominator, but I have written on the numerator. Yes. So there should be an inverse. There should be an inverse. Why it should be an inverse? Because this derivative, it's a scalar, so you can easily take it numerator, denominator, anywhere. But df is a matrix. It's a Jacobian matrix. Okay. So df, how df looks like? K bar, it looks like this. So you have at f, this is the stylish looking f. So f has all the components. Column, element of the matrix. So like this. So you partially differentiate dou f1 by dou x2, dou f1 by dou x3, so on. You keep on going till dou f1 by dou xn, because you have x1 to xn, right? Now the business of f1 is done. Now you have to catch f2. So carry on the next row. Dou f2 again by dou x1, dou f2 by dou x1, sorry, dou x2, so on till dou f2 by dou xn. The nth dou fn by dou x1, dou fn by dou x2, so on. Dou fn by dou x. Is it okay? So I am writing in a very general way, so no need to get afraid or anything. We will solve examples so you can appreciate better. But I want your brain to map to these things so that you can easily implement all the generalizing kind of ways to show that you can do it in Python. Implement just that in Python. Okay. Okay. Now you know the solution, isn't it? So if you are given a system of nonlinear equation, then what you do, just apply this red bracketed iterative scheme, and you are done. And you can solve. Okay. Shall we go to an example? Action. Yes. I will give a few minutes for you to digest this. Okay, good. So that's good. So let us start by an example, shall we? Let us solve. Let us solve the system of nonlinear equations. Given by All right, so let us let us revisit this problem again, and this will be the assignment for your next class. Okay. So as you see, both depending on x and y. So we want to use Newton Raphson method instead multidimensional Newton Raphson method to find the equation for this nonlinear system of equations. So as you know, we already have this iterative scheme, and this is our Jacobian matrix over here. Okay, and this is the inverse, which is a bit complicated form of this matrix, but this will be given to you if it is complicated. Okay, then nothing else. You have to just x1, and how I write it? X superscript 1, x superscript 1, y superscript 1. That denotes the first iteration value, and that is following this iteration scheme over here. You can see it is x0, y0, which you already know, which is being split into in two different batches for the two classes. Okay, and minus the inverse of the Jacobian matrix. All right, and then that is evaluated at the first guess x0 into multiplied by the vector of functions evaluated at the past value. Here also you can imagine how the future xk plus 1 past xk. In numerical methods, you will see this very often. The future depends on the past, except kind of Gauss seidel. Now you know how this method works. Now, how can you Python understand this and make Python do the stuff? Okay, let us see the Python version. Okay, so let me see what kind of equations I have taken here. Okay, so Python is solving another equation for you. Okay, let me write the equation. So in Python, equation I'm going to solve using Python is this one. X1 square minus 4 equal to 0, which you can see is a circle, isn't it, of radius 2. X square plus y square equal to 4. Yes. So, and the next equation is this one. So this is your F1, this is your F2. Your interest is to compute the solution using Newton Raphson. All right. Let us see this equation over here. So I am defining the exact same thing which I have written down on the board. So you can see it is x square, x0 squared, x1 squared. So x is a vector over here. The first element of the vector is the x component. The second element of the vector is the y component, that is the x2 variable in your equation. Okay. So x0 square, that we denote by double asterisk in Python. The power we denote by double asterisk in Python. X1 double asterisk 2, that means x1 square again minus 4, right? And this is the second equation F2, that is e to the power x 1 plus x2 minus 1. Yes. np.exp I have taken here. And it is returning the vector of functions. Vector where the first element is the function f1, second element is f2. You need it, isn't it, in your Newton Raphson? Can you see, is it needed for you in Newton Raphson method? If you see, you are multiplying the inverse of the Jacobian with the matrix. So don't worry about this. This you can easily get. The first row is dou f1 by dou x1. The second one is dou f1 by dou x2. Third variable dou f x1. Fourth one, dou f2 by dou x2. I have manually entered this. Fine with you? Any queries so far? Any queries? Okay. Okay, all right. So now you have the inverse. Now you can just use INV function in Python, right? INV of the matrix. Input will be the matrix. Fine. Let us see the Newton Raphson into action. So here x equal to x naught is the initial guess, okay, that the user will give. You can see down here the initial guess is 1, 1. Initial guess is that will be passed to this Newton Raphson function. Newton Raphson, I have written down function, okay. That means it will, based on some inputs, it will do some work inside the function and it will give you some output. That is the function role in Python. So what are the inputs this function takes? It takes the function input as f. F will be the Jacobian matrix it will take. Then the tolerance. You should tell that I want an accuracy of the root to 10 to the power minus 6 accuracy. Up to 6 decimal places, I want the accuracy to be. Accuracy of 6 decimal places. Of course, maximum iterations you are doing 100. Of course, that's not mandatory. You have just taken 100 iterations. Convergence is attained less than 10 to the power minus 6. Then it will break, as we saw in the morning class. Yes, with 20 iterations, it was finishing. Yeah. Let us go into this function value, x equals to x naught. Fine. You are doing the initial condition here, x equals to x naught. Then you are iterating this again and again till 100 iterations. But within that, computed this tolerance. If it is satisfied, it will break. That is return. It will come out of the loop. Okay. Again, it will return the value. That means it will come out of the loop. Okay. So delta x is the right hand side of the chunk, the chunk of this expression. That is the multiplication of the Jacobian times the vector function you are doing. Yes. So see, that's the same thing. Jx into comma minus fx. Can you see this? What is happening over here? This is a very nice concept he has applied. Oh no. Let us see this. You have xk plus 1 equals to xk minus df at xk inverse xk, right? F of xk. That is the squared one which I have written down here has been implemented in another way without computing the inverse. Without computing the inverse, he is trying to solve this. How? Think this and this. I think it reminds you of something like a ax equal to beef kind of form. Okay. Now, what is vk? What is vk? From this inverse f of x. Do you agree? So now if you use the dot solve function of Python, okay, which can solve ax equal to b, it can also solve nonlinear also. So therefore just solve it. Just and this as input. Then the output will be this quantity. And what is this quantity? It is this. Isn't it? It is this quantity, right? Which is what you need in which is exactly what you need in the method. So you can understand why I am writing this dot solve function there. Instead, you can also use the inverse function. No complication is there. You can use inverse function. You can just use INV of J. Fine. No hard and fast rule. This is another technique. I urge you next class, you try to solve without that. Use J INV function in Python. Using that you do, not this. Fine. Okay with this, right? Yes. So you can just see that I passed the initial guess 1-1, and I am calling Newton Raphson. How many iteration does it take? So here it is vector x1 and x2, fine. And the solution was attained after 6 iteration. Okay. Newton Raphson method is very powerful. This multidimensional Newton Raphson is very powerful. This simple method is being useful to me till now. Yeah. So let us see a visualization. Let us see a visualization. Okay, so I think I have taken the same equation. But instead of just showing the value and the answer, I am showing some curves and some place. Ran within 4 seconds. Okay, let's see. Why it is not working? Sequence of points which approach the root. The big dot you can see is the root. Oh, sorry. I have to run this. So you can see how many iteration it took. Okay, the Newton Raphson method it took. Okay, so you can easily see 1, 4. But before going after, so the big dot you are seeing some more iterations are being there. Suddenly locates the root. It is quite surprising, isn't it? And it is sitting in the three-dimensional space. It is sitting in the three-dimensional space, but it is behaving very much like humans. Yes, human just knows where the location is, and human just goes and attains it. So Newton Raphson, it just finds the root where it is located. It is quite interesting. So why it converges? Why it converges? That is a suspense. Okay, that is a suspense for your next semester. Okay, if I am going to, I will reveal this. Why? But mostly it is related to optimization. Mostly the answer is related to optimization, something known as gradient descent optimization, which is heavily used in your machine learning as well. So why this is happening in like how you can visualize this as a problem of optimization, saying that the roots, the distance between the two surfaces is minimum as possible. So that is equivalent to saying that find the root. Solving regression optimization, you will see next semester that regression problem can be transformed to optimization problem. Optimization problem will be transformed to regression problem. Sometimes optimization problem can be thought of as root finding problem. So if you know about root finding, solve some optimization problems. If you can solve optimization problems. If you know optimization, you can solve regression problems. Regression, optimization, this kind of Newton Raphson method, why it happens, gradient descent, all parts of machine learning tools. So if you know a reality check of these methods, how it works, then I hope you can easily understand the techniques when they straightforward apply in machine. So this is what I intended to cover today. Okay. So